Okay, after we finished the theory and the introduction of evolutionary algorithms, and after you have a good understanding of the idea of a fitness landscape, we will look into our very first optimization problem and the corresponding evolutionary solver implemented by the component Galapagos. We continue from the example that we've used for the fitness landscape that is generated for the minimum bounding circle that encloses a set of randomly generated points. And now I disable the preview because we know somewhere in the middle we have our optimal position of the point for our minimal enclosing circle. But the question is, where exactly is this point, and can we find a better one than with just filtering the best result from our 10,000 generated circles. So again here you see the setup. We manipulate here with the sliders the position of the center point for our enclosing circle. The circle is generated with this as the center point, controlled by these two parameters, and the radius is the distance to the point that is furthest away. So the largest distance is used as the radius. Now these two parameters, they are now used as genes. So that's probably the most simple version of a gene, just two numbers that represents a design feature of our phenotype, or that's a design parameter of our phenotype. You can see that genes, they are linked to the genome here in Grasshopper. Let me increase the Grasshopper window, and the genome of the Galapagos component. That's the Galapagos component, and you can link the genes that you have into this input. That's a very special input. As you can see, I move it from the genome input to the parameter. So that's the way how I link it. That's the first one, and by pressing the shift button, you see you can add another one with the plus. So here we have these thin red lines. They go to our genes that controls the position of the center point. And as a fitness value, we only can have one fitness value. So Galapagos is a single criteria optimization. Single criteria means you can have one fitness function, but of course you can construct your fitness value by summing up a set of fitness values characterizing your solution. We will look into this in later examples in this course. Now the fitness value, it's drawn again in a way that you link it to a value. In my case, I link it to the area that is computed for a circle with these parameters here. Yeah. So here in the output you see, if I change the position, the area is changed as well, and this is used as fitness value for this specific variant. So this circle is our phenotype. It's a design variant, or a variant for a solution of our problem. And we have two control parameters, two design parameters. Now this is all fine. The optimization, the crucial part and the most exciting part that you're waiting for, can be opened by double-clicking on the Galapagos component, which opens a pop-up window. the Galapagos editor. And here we can set up our basic parameters for our evolutionary algorithm. So all these things you have seen more or less in before in our theoretical explanation. We have two solvers, the simulated annealing, that's a more direct hill climbing algorithm, which we will not consider here, and our evolutionary solver, which we will use for this example. Going back to the options, we want to minimize our fitness value, means we want to find the smallest enclosing circle. You could also change it to maximize it, then you would find the biggest possible, or then you would look for the biggest possible enclosing circle, which would be possible as well. Here you can set up, or you can define the a termination criteria in terms of time. You can say I want to run this solver for 1 hour or 1 day or 1 week or whatever you want. And here you can set up the population, so how many parents per iteration are generated, respectively how many we use for the initial population, but this parameter primarily defines the number of individuals that are maintained after selection per generation. So that's the number of parents for the next generation. And here we generate 10 times as many variants for the initial population, which we use to set up everything. Right. That's more or less everything you need to know. And these are the crucial parameters. So the population, the more or the higher the number that you use here, the more variants you generate and the more you need to measure per generation. So it's not clear what's the best combination. If you should have bigger populations and maybe then you find the best solution in a shorter time with less numbers of generations, or you use a small population and you run more generations, which I do now. And then the solver, that's relatively simple. Here you can start your solver, and what's happening. Here you see a little bit the definition changing. What we have here are all iterations for all the variants that are generated. We compute the individual area values, and you see here the parameters that are set in the beginning randomly and later for all the variants that we have based on the crossover and mutation operators that are applied to our individuals. So here now we have the first iteration. You see the best chromosome in our first iteration is 139 in areas, in area units. Then we find in the second generation one with 133, which is the best for some generations. And we can wait now if the algorithm finds something better, and here are indeed 132. That's a smaller circle than the one we have found in our definition here by running a brute force algorithm or generating 10,000 variants. We have had 133 as the minimal size. Here we found one with 132. But you see now the solver converges into an optima. So probably we can stop it now. Means here we the algorithm climbed up to a mountain, to one of these mountains in our landscape. Respectively here in the visualization of this fitness landscape, we end up in our valley. You can look around here in the solver. You can increase the area that is shown here below, and here you see how many variants are in this or in the from generation 8 to 17. Here you have this fitness landscape diagram, an approximation, and here you have the chromosomes with the corresponding fitness value. So here we see a lot of very good, or the best variant is maintained over all the generations. And in the last generation we have our best one found so far here. Okay, that's basically what you need to know for the evolutionary algorithm for the Galapagos evolutionary solver in Grasshopper. And we will look into another example in the next session, but I would highly recommend you to play around with the parameters here and trying to change the fitness values, trying to change the measures or adding another parameter. So experiment with this definition in order to learn how you can use this optimization.